Greetings, college physics students. So I'm making this video to help you out with your homework. Unit 1-1, numbers 9, 11, and 12 we're going to discuss. I'll start with number 9. Okay, it says a graph of position versus time is given below. Find the average velocity over the following time intervals. So you should be looking at a picture that looks something like this. I left some of the detail out. Now, remember that velocity, your average velocity, is delta x over delta t. An important thing to realize is that's a slope of an x over time graph. Or I should say that's the slope of an x against time graph. So these questions are all slope questions. So 0 to 2 seconds. So 0, 0 is here on the graph. 2 seconds, I'm looking at the picture, is here. And what you're going to have to do is read the coordinates of this point off. In the graph I'm looking at, that would be the point 2 seconds and 10 meters. Yours might be different. They may have gave you different numbers there. So we're looking for the slope of the line between these 2 points. So you take y2 minus the y value here over x2 minus the x value here. Now, question 2 says from 0 to 4 seconds. 4 seconds on the graph is here. I'll do this in green. Now you're talking about the slope of the line between these 2 points. So you're talking about the slope of this, and you may wonder, is that okay that this doesn't lie on this curve? And the answer is yes. It's the slope of the line between this point and this point, and that's all you need to know. And I'll let you fill that out. And from 2 to 4 seconds. So 2 seconds on the graph is here. 4 seconds is here. Again, the y coordinates for that, at least on my picture, are around 5 meters, and the y coordinate here around 5 meters. So you're looking for the slope of this line and so forth. That ought to get you through number 9. Okay, let's talk about number 11. Let me clear this up here a little bit. Okay, it says a jet has a takeoff velocity of 73 meters per second, and it accelerates at about 1.9 meters per second. So what we're talking about is a jet. So start by, sketching a picture of what's going on. This is going to be a crude picture. I guess we'll do it in green. Here's my jet. It's on some sort of runway. It's accelerating. So remember the motion diagrams, the snapshots in time. Click, 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 click. So the motion diagrams might look something like this. So there's an acceleration given in the problem. Write that data down. In my problem, it's 1.9 meters per second squared. Yours, this might be a different value. It says that there's a takeoff speed of 73 meters per second. So in this problem, I'm going to call that a final velocity. This jet has to get up to 73 meters per second to take off. This number may be different in yours. So start with a picture, right? And again, when you go through about all of my videos, you'll see a pattern here. We're drawing pictures. We're using the dots here to tell us a little something about what's happening to the velocity. We put in a coordinate system. Here, I'm going to call this the plus x direction. So my jet here, if you will, is starting at the point 0, 0. Okay. Then, remember the 3 graphs. And a lot of times I only draw 2 of them, but let me go ahead and draw 3 of them. All right, and again, remember, I'm still trying to get used to this new screen here. Okay, so acceleration is constant out to any time t here, and it's some number. All right, you have the numerical value here. When acceleration is constant, your velocity graph is linear. And it's starting with a velocity of 0. Draw this graph. I don't want to do that for you. Again, this is your homework assignment. Then you use this graph to get the equation for this one using this fact. Remember, acceleration's delta v over delta t. So your delta v is acceleration times delta t. Now, change in velocity is v final. I usually just call that something like v. Minus the initial velocity of this jet is 0. Okay. Oops. Getting used to a new pen here. This, remember, is this area here. Now use your graph, how you label it. The area is going to be whatever you call this times whatever you call this, right? That should give you a linear function for V. I don't want to draw that again. This is your homework assignment. The next step here, once you have this, right, you're going to use an area under the curve here, like I've done in lots of videos here, and you're going to set delta x equal to that area. You're going to use this to get your equation for x. It should be quadratic. Now, oh, you know what? To tell you the truth, I'm going to back up on my directions here for a little bit. We don't actually need to develop equations. Everything I set up to this point, by the way, is just fine. You could do this exactly the way I was talking about, but I'm going to back up and talk and simplify it a little bit as well. Let's go back to this velocity graph. The change in velocity, you can just use this numerical value if you want. So for example, the acceleration, which is given, is going to equal delta v, given in the problem, over delta t. And here you can solve for your delta t. Now when we go up to this point right here, when you get that position function, the delta t is now a known value, and you can put that in to calculate x, the how far. So all the directions I just did were perfectly fine. Use this area to get an equation for this. Use the area here to get an equation for this. Then I would just come back here and, here's what your acceleration's equal to, given, calculate your delta t, and use that here to get the final velocity and here to get your final position. So I probably beat this one to death enough. Hopefully that'll get you through number 11. All right, let's talk about number 12. Two cars traveling in the same direction along a straight highway, one at 55, one at 60. All right, let me get rid of this stuff here. So picture, the old saying, a picture's worth 1,000 years. I like to say in physics it's 2,000. Or let me restate that. Picture is worth 1,000 words. In physics, it's 2,000. So let's do like a top view, and I'm going to call this one car A and car B. And I think they start out at about the same spot. Let me see here. Two cars traveling the same direction. Assume they start at the same point. How much sooner does the faster car arrive at the spot 13 miles away? Okay, so this is a constant velocity problem. The velocity of car A, 55 miles an hour. Yours may be different. Velocity car B, 60 mile per hour. All right, and what I would like you to do now is draw velocity and position graphs for both cars. Now, miles per hour and hours, those are not gold standard units for physics, but I think they will work just fine here. I would probably just, if I were doing it, I would leave that 55 mile per hour the way it is and leave the 60 mile per hour, because the distance given was in miles anyway. All right, so your velocity graph for car A is going to look like this, and this is going to be true out to, let's say, any time t. This will be a number, okay, that you're given in the problem. And in my example, it would be 55. Your position graph for car A will be linear. And again, if we call this x equals 0, whoops. Like I'll put a coordinate system here and call this plus x. Right, this will be linear. And use this area to get the equation for this line. X equals, you're going to have a number times t. It's really reasonably simple. I'm not going to do all the detail for you. You're going to have two more graphs for car B. Now, you should be able to get a position against time for car A and do the same thing for car B. So you'll have x equals, again, a number times t for car B. Now, car B is going to win. Use the distance given in your formula here for car B. Use it for your final position to get the time. Then take that time and put it into the formula for car A. And that will tell you where car A is, and then you can start answering the questions. Now, one thing to keep in mind here, as far as answering the questions, by the way, let's see, assuming they start at the same point, how much sooner does car A arrive? arrive. Okay, so my final description here, let me back up. Use your total distance here, given in the problem, to get a time for car A. In the similar formula for car B, put in the same distance, get a new time, and the difference between those times will answer your question for A. Now keep in mind that in these units you're going to get a time in hours, but if you look at the thing it says in minutes, so you're going to have to do a unit conversion there to answer part A. Okay, part B is kind of a little bit trickier question where it says how far must the faster car travel before it has a 15-minute lead on the slower car? In my example, A was the slower car. So a 15-minute lead would be this. And I'm going to take this equation and just rewrite it. Oh no, I'll just leave it alone. All right, so x equals a number times t. 15-minute lead, this would be a quarter hour, 0.25 hours. Calculate this. That's how far that car went. So what that will be is that's the lead. That would be like how far it would take car A to travel in that 15 minutes, basically to catch up to car B. Give me a second here. Now, once you know that, you will know how far in front car B is than car A. So, like, if I were to keep drawing these pictures, let's say B is here going this way, and A is maybe here, the slower car going this way. This distance will be what we just calculated. So now, once you know that time, calculate this distance using this formula here. And that should tell you how far that thing has traveled. And that should be the answer to number 12. So, all right, not the best set of videos I made, but hopefully it will get you through these questions here. And again, if you still have trouble, just send me an email and I can redo the videos, all right? So I hope that helps. Have a great day.